Hi Calculus, welcome back. Our objective today is going to be to calculate some basic derivatives by hand. I'm going to force a pause on your screen, make sure you've got everything on the checklist, make sure you are on full screen mode. Alright, go ahead and pause your screen and try this warm-up for me, and then when you're ready, go ahead and unpause with a different color, and let's check your work. Alright, I'm going to ask that you pause your screen one more time and double check your work. Remember that if it looks good, then put a little check with your second color. If not, put the correct answer with the second color. Be very mindful of this one in particular because that kind of rewriting comes up a lot in calculus. Alright, go ahead and pause your screen. Alrighty, so I have some functions here on the left as well as their derivatives on the right-hand side. And I'm going to ask you pause your screen again and see if you can spot the pattern, how to go from f of x to f prime of x, given that f is some kind of power function, so x to some power. Alright, so go ahead and pause your screen, take however much time you want, and see if you can spot the pattern here. Okay, we are back. So, what do we think? Maybe the first thing you noticed was that your powers drop by 1 each time, right? So, if I start with the power of 2, my derivative has a power of 1. I also notice that my old power, this 2, is my new coefficient, right? So let's try that pattern again with the next one. So if I take this power and multiply it to that number, that coefficient, my new coefficient is 9, right? And then what do I do with the exponent? I drop it by 1, right? I started with a 3 power, and then I should subtract 1, I should get a 2. Okay, let's take this next one. I'm going to fly that 5 to the 4, so 5 times 4 is my new coefficient of 20, and then subtract 1 from 5, and now my new power is 4, okay? Notice that it works with sums and differences as well, okay? So fly the 2 to the coefficient, my new coefficient is 4, drop the power by 1, so I had a exponent of 2, my new exponent is 1, okay? Fly the 3 to the 5, my new coefficient is 15, and drop the power by 1, my new power is 2. Okay, now it still works here. It maybe looks a little bit funky, but notice my understood exponent here is 1, and my understood exponent here is 0, right? So it works. Similarly here, my understood exponent is 0. 0 times 13 is 0, okay? However, with these two, really think about what the derivative gives you. What does the derivative give you? It gives you the slope of the tangent line, but notice those last two functions were what kind of functions? They're both already lines, right? So if you'll notice, this function, if I put a y equals there, is a line with slope what? Yeah, the slope is always 0, so that means that the derivative function, the slope is always 9, so that means the derivative function is always going to be 9. Similarly here, is the one I was thinking about. Take a look at that. That's just y equals 13, so horizontal line through the y-axis at 13. Its slope is always 0, so its derivative should always be 0. If you take a look at the other ones we had, their derivatives had an x in them. So why do you think their derivatives vary? They have this variable of x. Yeah, because the original functions, their slopes are going to vary depending on what x value you are at, where you decide to zoom in on the graph, right? But the last two are lines. It doesn't matter where you zoom in, the slope is always going to be the same. So that's why their derivatives are constant, okay? All right, so let's generalize. This is what we call the power rule. So this is how we're going to write it. If f of x is equal to x to some power n, then how would we generalize f prime of x? Well, remember, you're going to fly the power to the front, so my new coefficient is whatever my old exponent was. I still have x, and then what's my new power? Yeah, it's going to be n minus 1, my old power minus 1. All right, make sure you've got that written down. Okay, so before we get going on examples, remind me, what does the derivative give us again, and why do we care so much about the derivative? So the derivative gives us what? Gives us the slope of what line? The tangent line at any x value, okay? So if I have f of x and I can get f prime, the derivative, then I can plug in any x value to f prime and it'll automatically tell me what the slope is of that x value. Why do we care so much about slope? Well, slope answers a really important question in real life applications. Slope answers the question, how fast? Okay, and that's a really important question to answer, like how fast are we making money in our bank account, right? How fast is a virus spreading? So these types of questions are really essential to mathematics and really to any life application you have in math. All right, I'm going to force a pause on your screen. Can you please copy the two f of x's that I have on my screen? All right, let's try the first one together. So f of x is 3x squared plus 2x minus 5. So always, always, always label what you're finding, in this case f prime of x, okay? Really make sure that you're communicating well mathematically. All right, so I can go term by term. So if I have this 3x squared, remember I can fly that 2 to the 3. That 3 coefficient just comes along for the ride. So I have 6x. Now what's my new power? My new power is 1, right? And I don't have to write it, but I'm going to just write it now for emphasis. Okay, let's go to my next term. I've got a plus 2x. So again, you can think of that as 2x to the power of 1. So if I fly the 1 to the 2, I just get 2x to the 0, and x to the 0 is 1. Another way to think of that is this is a linear term with slope 2. So the derivative of that term is always going to be 2, the slope. And then finally minus 5, that's a constant, right? Again, you can think of it as x to the 0, flying that 0 to the 5 makes the 5 go away. Or you can think of it as 5 is a constant term, and the slope, again, of a horizontal line, a constant linear function, is always 0. So your constant terms are always going to go away. I'm going to put plus 0 here for emphasis, but in the future, just don't write the derivative of those constant terms, okay? All right, I'm going to force a pause on your screen. You try the second f of x, and then hit continue when you're ready with your second color to grade. I do want to make note that pi, a, and b are all constants. All right, answer is on the screen, so check your work with mine, and then when you're ready, let's go ahead and continue to the next part. All right, I'm going to force a pause on your screen. I would like for you to please copy the table and then hit continue when you're ready to go. Okay, we're back. Let's go ahead and fill in this table. I'm going to do the first column with you, and then I'm going to ask that you finish the rest with your calculator. All right, so I'm going to use Desmos. Feel free to use an 84. So I typed in f of x equals e to the x, and then I would like f of negative 2 as well as f prime of negative 2 for that first column. So I'm going to go and put those values into our table. All right, so remember, you can truncate, you can chop it off after 3 decimals, or you can round after 3 decimals, but I do need at least 3. And I'm going to force a pause on your screen now and ask that you fill in the rest of your table, either with Desmos or an 84, and then when you're ready, grab your second color and we will check the table together. Okay, so hopefully this is what you got or something similar. I tend to truncate. If you rounded, your third decimal might be a bit different on some of them, and that is totally fine. But what are we noticing here? Do you see that everything in this row is the same as in that row, right? It didn't matter what my x value was, no matter what x value I chose, f of x was the same as the derivative, right? Which is really pretty wild. This is the only non-zero function that has this property that f of x is the same as f prime of x, okay? In other words, whatever x value I pick, the y value there is exactly the same as the slope. So let me show you an example. Here is our function f of x equals e to the x, exponential growth, right? And I picked a value that gave me a nice output. So when x is 0, y is 1. Now, when I zoom in on that point, till it starts to look linear, you can see it already. Go back. What's the slope there? It's also 1, right? And that would happen no matter what x value I chose, okay? So if I were to zoom in here, then I would get that the slope would be what? The slope right there would be 2.732, okay? And that is unique to e to the x. All right, so please write this in your notes. The derivative of f of x equals e to the x is what? It is itself. It is also e to the x, okay? And this is Mrs. Peterson's favorite function because it is the only non-zero function whose derivative is itself, okay? We can write this in Leibniz notation as well. We can say d dx, so that means the derivative with respect to x of e to the x is what? Is e to the x, okay? So go ahead and pause your screen, write what you need to write, and then we'll move on to a couple more examples. All right, I'm going to force another pause on your screen. Can you please copy the 3 functions that I have, and then we're going to take the derivatives together. All right, the first thing I want you to notice, all 3 of these are going to require some kind of rewrite before we jump into finding f prime, because none of these all have x or t to some power yet, okay? Also, before we get started, I want you to notice the difference between a power like x to the 2 and an exponential like e to the x, okay? So if you'll notice this, where is your variable? It's in the exponent, right? But if I have this guy, my variable is where? It's in the base, okay? So for something like this, I would use power rule, where I would fly the 2 to the front and then drop the power. And then how would I take the derivative of e to the x? Yeah, it's the best function ever. Its derivative is e to the x, okay? All right, so let's go ahead and start with f of x over there. So f of x is the cube root of x. Okay, so I first need to rewrite that as x to what power? X to the 1/3 power. Okay, is that the derivative? No, we have just done some algebra here to rewrite, okay? Now let's do the calculus. So now I'm going to call this f prime of x. I'm finding something new, right? And we're going to fly that power to the front. And then I have x, and now I need to subtract 1 from 1/3, okay? So 1/3 minus 1, common denominator here is 3, so that's going to be negative 2/3 as my new power. And you're just going to leave it like that, okay? You do not have to rewrite back. You can just leave it with your exponent as a negative in fraction, okay? All right, let's try g of x. Okay, what term or terms do we need to rewrite? We need to rewrite that first term, correct? So I'm going to rewrite that as x to what power? X to the negative 2. And then I still have e to the x. Okay, that just comes with me. I need to keep it as is. Is that the derivative? That's not the derivative. That is just rewriting. That's just using some algebra. So now make sure you don't start putting equals and take the derivative. That would be a linkage error. Make sure you state now what you're finding. Now I'm going to find the derivative, g prime, okay? So now, term by term, I'm going to fly the negative 2 power forward. What's my new power? Be careful. My new power is negative 3 because negative 2 minus 1 is negative 3, okay? And then what is the derivative of e to the x? Yes, itself, right? The best function ever. Makes our life easy. Okay. You thought you hated it in Algebra 2 and Pre-Calc, and now you will love e to the x in calculus. Okay. Last one. Which term or which terms do we need to rewrite? We need to rewrite the second and third terms. The first term is good. I already have t to some power. How would I rewrite 1 over t? Now think about that as 1 over t to the 1. So if I bring that up, that's going to be t to the negative 1 minus, and how do I rewrite a square root with a power? T to the 1/2. Okay, good. You know what I'm going to ask next? Is that the derivative? That's not the derivative. That's just doing some algebra. So now s prime, all right, fly that 2. My new power is 1 minus, fly the 1. That's my new power. My new power is negative 2 minus, fly the 1/2 forward, and then subtract 1 from a half, so that's going to be negative 1/2, and that's our final answer there. All right, as I said earlier, I think that a really classic calculus problem is to ask you to write the equation of the tangent line. And when they ask you to do that, always just keep it in point-slope form, okay? You never have to go ahead and get it into slope-intercept form unless you need that for another part of the question. We can always leave our answers in point-slope form. So as a reminder, x1 is typically what's given. If y1 is not given, I can always find it by plugging my given x value into f of x. And then how do I find the slope of the tangent line? How do I find m? That's going to be the derivative, right? Evaluated at that x value of interest. All right, so for example 3, can you please write this f of x? And we're asked to write the equation of the tangent line, so as soon as I see that, I think, oh, point-slope form, okay? At the point 0, 2, so they've already given me x1 and y1, right? 0, 2. Then write the equation of the normal line, not life, normal line, which is just another phrase for the perpendicular line at the same point, and then we'll verify with our calculators, okay? All right, so f of x is this guy. That 3 is a little bit bothersome. However, let's just go ahead and divide both terms by 3, okay? So I've got 6 over 3 is 2, so 2 e to the x plus, and then I'm just going to leave that as 2/3 x, okay? All right, so I've got my x1 and my y1. All that's left to find is what? Is the slope. So how do I find the slope? I find f prime, the derivative. So f prime of x, term by term, that 2 just comes along for the ride, okay? The derivative of e to the x is e to the x. And then what's the derivative of 2/3 x? So that's just going to be 2/3. See, that's a linear term with slope 2/3. So the derivative of that term is just 2/3, okay? Now, where do I want to evaluate this at? What x value? At 0, okay? So I have 2e to the 0 plus 2/3. E to the 0 is what? Is 1. So I have 2 plus 2/3. Getting a common denominator here would be 3, so that'd be a 6. So I'm getting 8/3. Okay? All right, so for the tangent line, we have y minus y1, which remember from up here was 2, equals m, what's my slope? That's what we found to be 8/3, times x minus x1, again up here was 0. You don't have to write that, I'm going to write it for emphasis though. The normal line, how do I find a perpendicular line? Negative reciprocal of the slope, right? So everything's going to stay the same, except I'm going to take the negative reciprocal of my slope. Okay, let's take a look at the graph. All right, here's our original function with our point of interest. Here is the tangent line we found. Looks great. Again, if I zoom in enough on there, the red and the purple start to look the same. And then here's the normal line, should be perpendicular, and that looks great as well. All right, here's our last example. I'm going to force a pause on your screen. Please go ahead and try this one and bring it to class.